All right, so section 12.4 is called Implicit Differentiation. And what we've been doing is we've been differentiating explicitly, but it's one of those lazy math things where since we do it so often, we just don't say explicit differentiation. What's going to happen is we're going to use implicit differentiation whenever we don't have a function. Okay? So basically, how do you know I don't have a function? A kind of cheap and dirty way to do it is to just say if you have y's involved and there's an exponent other than 1, it is not a function. And so instead of us trying to fight through this crap and see what's going on, let me give you an example. This is an equation of a circle that is centered at 0, 0, because there's nothing being added or subtracted to x and y, and its radius is 3. Okay, so this is the equation of a circle. For me to differentiate this, I would have to get it in function form first. So I would have to solve for y. So that would give me y equals 9 minus x squared, and then I would take a square root. Okay, so this is in function form. The positive part of the root is the top part of the circle. The negative part of the root is the bottom part of the circle. And put it together, it makes a circle. So if I were to differentiate this, I would have my derivative is 1/2 9 minus x squared to the negative 1/2 times the derivative of the inside, which is negative 2x. And that negative would flip-flop this plus and minus. And so you can effectively just ignore it. All right, so your derivative is messy and nasty. Implicit differentiation, and here's the tricky part, is whenever I take the derivative of a variable, I'm going to indicate that I've done that by putting d variable by it. So if I take the derivative of x squared, I'm going to ignore all this hard stuff, and I'm going to come down here. So this is implicit differentiation. I've got x squared plus y squared equals 9. I'm going to take the derivative of x squared. So the derivative of x squared is 2x. But I took the derivative of x, so I need to note that by saying dx. So this is one thing. It's a package deal. And that says 2 times x times dx. What it means is the change in x. Okay? So plus 2y and then dy, and that equals 0. So your next step is get your dy's on the left and your dx's on the right. Okay, so he has a dx. I'm going to move him to the right by subtraction. So 2y dy equals negative 2x dx. All I did was subtract him over. And now I need to get dy dx by itself. So again, this just means the change in y. This means the change in x. So what I can do is divide both sides by dx. So it'll disappear from the right and appear in the denominator on the left. And then I can divide both sides by 2y. So it'll disappear on the left and appear in the denominator on the right. So now I found out that dy dx is a negative x over y. So that's what we're going to be doing. You just got to remember there's 3 steps, essentially. Take derivatives. Your constants will always go to 0. Whatever you take a derivative of, make sure you note it by putting the derivative of x or the derivative of y. Step 2 is going to be get your dy's on the left and your dx's on the right. And then your last step is going to be make sure your dx is on the left in the denominator, and everything over here will be on the right in the denominator. So, that being said, problem number 1 in 2.4 says I have a 2x plus a 3y is 9. Okay? So I'm going to use implicit differentiation to find this. So the derivative of 2x is 2 dx. The derivative of 3y is 3 dy, and that's going to equal 0. Step 2, get your dx's on the right, and you leave your dy's on the left. So I have a 3 dy equals a negative 2 dx. Okay? Divide both sides by dx. divide both sides by 3. So you find out that dy dx is a negative 2/3. So what are you finding? This is a line. Okay, if I had written that in slope-intercept form, you would have had 3y equals a negative 2x plus 9. Divide everything by 3, y equals a negative 2/3 x plus 9/3, which is 3. But all I care about is what's your slope. Your slope is a negative 2/3. So you just found it implicitly using implicit differentiation. Of course, it's not always going to be that easy. So let's do another one. We have x to the 8th plus y to the 5th. And that is going to equal 39. So this is not a function. How do I know it's not a function? Because I got a variable attached to my y. So differentiating implicitly, take this derivative. He's an 8x to the 7th dx plus a 5y to the 4th dy equals 0. Everything with a dx needs to be on the right, so I'm going to move him over. So 5y to the 4th dy equals negative 8x to the 7th dx. Divide both sides by dx. And divide both sides by 5y to the 4th. And that is your answer. So being a smart aleck that I am, I always say do the flippy floppy here. So you're going to have a dy dx, so take this and put it here, and take this and put it here. So do the flippy floppy. You're going to flip flop those two places. All right, so let's try another one. We've got 5x squared minus 5y cubed equals 2. And I want to differentiate implicitly. So take this derivative, I get a 10x dx minus a 15y squared dy equals 0. Okay, get your dx's on the right and leave your dy's on the left. That gives me a negative 10x dx on the right. And then do your little flippy floppy. So dy dx equals a negative 10x over a negative 15y squared. Your negatives cancel, and I can kill a 5 out of everything. So that gives me a 2x over a 3y squared. Okay, let's do product rule on one of them. So I have x to the 7th y squared equals 3. So this time I'm going to have to do product rule. So I have the first, which is x to the 7th, times the derivative of the second. So the derivative of y squared is 2y dy, plus the second, which is y squared, times the derivative of the first. The derivative of x to the 7th is 7x to the 6th dx. So first times derivative of the second plus the second times the derivative of the first equals the derivative of 3 is 0. So if it's got a dy, leave it on the left. If it's got a dx, kick it to the right. So I'm going to rewrite this a little bit. I have a 2x to the 7th y dy equals a negative 7x to the 6th y squared dx. And now I can just do the flippy floppy, which is really not the proper way to say that. Negative 6x to the 6th y squared over 2x to the 7th y. You can reduce it. I've got it set up to accept unsimplified answers as correct. So you could just leave it like that if you want to. If you want to reduce it, it would be a negative 7y over a 2x, because 6x's would reduce with one left over on the bottom, and 1y would reduce with one left on top. Okay, let's do one more. We have, wrong way. Let's do something fun. All right, we've got a, I don't know, 4 times the natural log of x equals 12 minus the natural log of y. And I want to do this implicitly, so 4's job is to come along for the ride. The derivative of a natural log is the derivative of the argument over the argument itself, dx. The derivative of 12 is 0. And then negative, the derivative of a natural log is the derivative of the argument over the argument itself, dy. Okay, so everything I've said just kind of sort of went to pot. I want dy to be by itself. He's got to be on top. I'm going to go ahead and flip everything. So I'm going to add this side over and subtract this side over. Okay? So that's going to give me a 1 over y dy equals a negative 1 over x dx. All I did was flip them. And now I can do my flippy floppy. So dy dx is a negative 1 over x over a 1 over y. And again, you can clean that up if you want to. A fraction over a fraction means that you would flip and multiply. So I would have a negative 1 over x times y over 1, which would give me a negative y over x. And that would be your final answer if you wanted to clean it up. All right, so let's try one more. I've got 9x squared minus 5y to the 5th equals 2x minus 5y. And I'm actually going to evaluate this one at 0, 1. Okay, so implicit differentiation. This is an 18x dx minus a 25y to the 4th dy is a 2 dx minus a 5 dy. I want all my dy's on the left and all my dx's on the right. So he's going to go. Okay, he stays. So I have negative 25 y to the 4th dy. Bring this one over, so he's a plus 5 dy equals a 2 dx minus an 18x dx. So I just brought him over by addition, and I pushed him over by subtraction. These ones stayed where they were. Okay, now if you can't combine them with like terms, which they're not, factor out your dy. So negative 25y to the 4th plus 5 dy is a 2 minus 18x dx. So I just factored out what was common. And now we're back in flippy floppy mode. So I've got dy dx equals, that's your numerator. That's your denominator. And that's the formula for instantaneous rate of change, or the formula for slope of the tangent line. So now what I want to do is evaluate it at 0, 1. So wherever there's an x, I'm going to put a 0. Wherever there's a y, I'm going to put a 1. So that gives me 2 minus 18 times 0 over negative 25 times 1 to the 4th plus 5. So that gives me a 2 over 1 to the 4th is 1. Negative 25 plus 5 is negative 20. So I get a negative 1/10. So that's the value of the slope of the tangent line on this graph at 0, 1.